Yeah, so let me start by thanking the real organizers for creating this fantastic, inspiring workshop in this beautiful place, in this very nice time of year, except for yesterday rain. um, so, recently I've been involved in 3 projects with terrific collaborators, Ted Erler, Matěj Kudrna, Jakub Vošmera, and all 3 of them got to speak here and describe our work. So I have nothing really new to say. So therefore I was asked by Carlo to give you a brief overview of the progress in the field of classical solutions in string field theory. And since this is a review, I have to apologize to the frequent participants of string field theory conferences that you may recognize some slides here and there, or you won't learn too much new stuff. So, so as has been stressed repeatedly during this very nice workshop, there are many problems in string theory for which string field theory is the most natural and possibly the only useful tool that you can address those things. So there are many problems in string theory where this can be used, but in this talk I will focus on the physics of classical backgrounds, which we need to understand, which we need for understanding what happens to unstable systems with tachyons, for example. We can also use the knowledge about these classical solutions to draw some correspondences or relationships between various backgrounds. The most trivial example of that is like backgrounds connected by marginal deformations. Less trivial examples are backgrounds connected by RG flows. We can also apply to time-dependent processes where this seems to be the only viable framework. So this is the brief summary of this talk. So for most of this talk, I will talk about classical solutions in open bosonic string field theory, which is the most beautiful one, the most developed one. But there is a spring coming in open superstring field theory with many new results coming in as we speak, as we meet. So, and we will hear also more talks on this subject from other speakers at this workshop. Well, closed bosonic string field theory is just a very sketchy, unfinished subject with some useful hints, whereas closed supersymmetric string field theory is a monster that we have to still tackle. Okay, so brief summary of what has been achieved. So in this beautiful open bosonic string field theory, so it's now we celebrate 20 years since the first meaningful solution found by Ashok Sen and Barton Sviebach in 1999. And this has been since then generalized to all sorts of universal and non-universal solutions. And there are, of course, a counterpart of analytic solutions, which are either wedge-based or KBC algebra-based or generalizations thereof. For the open supersymmetric string field theory, there's been also like a lot of numerical progress. Actually, most of the works, if not all of them, were written or appeared in the archive between 2000 and 2001. I haven't found a single thing after that, or I'm not really aware. And there were some non-trivial things, of course, tachyon vacuum, lumps, but also some things like D0, D4, studied by Justin David, very interesting paper. And there are some first appearances of analytic solutions, starting with Ted Erler for the tachyon vacuum in the Berkowitz superstring, and some marginal deformations constructed by Carlo and Alberto Merlano, and later revisited by Ivo Sachs. This is a very interesting, controversial subject that I would like to make a publicity to, and you will hear a talk by Ivo, and hopefully there will be very useful discussion. Okay, so closed string field theory, I have really nothing to say except to remind you that there's been a host of numerical work, like in the from the very old days to like up to 2008, by Belopolsky, Zwiebach, Yuji Okawa, Haitan Yang, and Nick Meller. And this concerned construction of tachyon vacuum lumps, of course, without understanding what that should really mean, whether it's some condensation in the number of dimensions of space-time, or what it is very unclear, just very sketchy. And of course, twisted tachyon condensation, which seems to be the most well-grounded, but still, I think it's not fully universally accepted or understood. And finally, for the beast, the only thing that I'm aware of is the paper and the very nice talk that we've heard by Shi-Yin during the focus week on the marginal deformation for strings in ADS3 background. So that's about what we can do. So this is the outline of this talk. So I will have one slide overview of string field theory, just in case there is some student who've never heard anything about that. Then I will review construction of universal solutions in open string field theory. Then I will move to non-universal solutions, and I will explain or review the relation to boundary conformal field theory and why that is interesting. And also I will also discuss some numerical approaches. And then I will move to a big chapter of analytic solutions in OSFT. And actually I decided not to talk about defects, and I have hidden transparency. But it will not show up. Okay, so this is the one slide on Witten's open bosonic string field theory. So we need a Hilbert space of some boundary conformal field theory that specifies the boundary conditions of the open string, some arbitrary but fixed conditions, given a bulk CFT. So we have some boundary CFT with some associated Hilbert space. We have the star product, BRST charge that all form some structure called differential graded algebra. Then we need a trace. We have the natural axioms. Then this Witten action has this nice, huge gauge symmetry. Size, ghost number 1, there is natural ghost number grading, the usual things that I assume everybody knows. Okay. So let me start by reviewing these universal solutions and in particular numerical approaches. So it may seem like from the perspective of the beauty of open string field theory, this is like using a rather heavy tool to tackle the problem of solutions. But anyway, it's a very efficient tool. And this work will be based on mostly on my work with Maciej, who is here, and he will talk about related things. Okay. So as I already mentioned, this year, in December, it will be 20 years since Ashok Sen and Barton Zwiebach decided to test celebrated sense conjecture that claims that the value of the open string field theory action at the critical point corresponding to condensed tachyon is exactly cancelled by the tension of a D-brane on which the open string field theory is formulated. And the tension can be calculated by different means, like, for example, by considering like an exchange of closed string and computing the one loop open string diagram. So this is a caricature how that works. This is actually example taken from their paper, truncation to level 2. They consider this as well as a truncation to level 4, which is much more laborious, and I think it would be very hard to repeat that by this computation by hand. No one would do it probably these days. But anyway, this is the calculation they did. So they plugged the string field into the action. So appropriately normalized the action for this three component field looks something like that in this level 2,6 truncation, and they found a critical point. Well, one critical point, which is like close to the critical point that you would get from like level 0 part, and for this the D-brane tension is cancelled within 95%. So and they repeated the calculation to level 4,8, and they got like 99%. So this was the beginning of level truncation in string field theory. This is where it attracted a lot of interest in the community, and many papers suddenly started appearing. So this is as time progressed. So people were trying to bring this calculation to higher levels. So like 1 year after, like employing Mathematica, Nick Mellor and Woody Taylor at MIT, like moved to level 10, actually using some oscillators in the flat space. Then Gaiotto and Rastelli, another 2 years later, used the universal basis, programming the conservation laws for the vertices, and they got to level 18. And they already observed that the value, actually it was predicted by Mellor and Taylor that the value will overshoot at some value, but now that they have seen it. And Gaiotto and Rastelli predicted that around level 27, the trend should return, that the overshooting start to decrease. And this is actually what we observed with my student Matěj Kudrna by doing the calculation few years back. It was actually published only in the appeared in the archive only in this December. That at level 30 we actually get this value which is closer to -1 than this value. So of course each step in the level was much more tedious because the number of states grows exponentially with the square root of the level. So there is a large increase in the demand of computational capacity, the CPU and the disk space for storing the vertices. So every time people wanted to move to a next stage, they have to employ like some different trick. Like for example, these guys did everything in Mathematica. Davide and Leonardo went to C++. Kishimoto and Takahashi went to supercomputers, etc. And we applied parallelism and SU on one basis, essentially. Yeah. So these are the critical ingredients for this numerical approach to level truncation. So first you have to, if you want to go to as high level as possible, you have to somehow minimize the basis of states that you work with, just to figure out the minimal number of fields that you need to consider, so that the equation of motion can be consistently solved. So you use universality, twist condition, appropriate gauge fixing condition, SU11 singlet condition, which is something that arises quite mysteriously in the Siegel gauge. Then we had to develop some new algorithms for calculation of vertices, especially the ghost vertex in the SU11 singlet sector. Then, like for the tachyon vacuum, this would not be a problem because we can take just the result from the previous value, and we have good starting point at level 0. But for other solutions, if there are any, we have to find a good starting point for Newton's method, and then we had to, or especially Matěj was great in developing several algorithmic tricks. Employing parallelism, which brings many unexpected obstacles, and And what is also important is having good observables, because these solutions, like at level 30, you have like roughly like 100,000 coefficients, 100,000 equations in 100,000 variables. So you can imagine you have 2 to 100,000 solutions, and you need some good observables to really find the useful solutions and the physical ones. And actually, it turns out that the number of really nice solutions is much smaller than 2 to the 100,000. It's actually around 6. And then, of course, what is important is to get as much as possible from the numerical data by solid fits to infinite level. Okay, so this is some sketch of observables, because this is something that has not been so appreciated in 1999. The prominent observable is, of course, the energy that comes from the action just by plugging in the time-independent solution. And then there is a object, some gauge invariant quantity, first introduced by Hashimoto Izaki and Gayoto et al. It's called Elwood invariant because Elwood understood what the value should be. And this was proved in some context by Baba and Ishibashi that this object actually gives the same quantity, gives the same value of the energy as this one for exact solutions. So when we solve equations of motion in Siegel gauge, we are not guaranteed that this whole object, that this whole string field equation of motion will be 0, because we solve only its projection to Siegel gauge states. And therefore, we must make sure that some contractions with some states outside, or like arises by taking a variation of the action with respect to fields which are not in Siegel gauge, that those variations are 0 too. And so in principle, there would be infinite number of constraints, but we looked at the lowest non-trivial one, which is given by this one. So, and we decided to measure this quantity for all numerical solutions to tell us how reliable they are. And there are some other ratios or some other quantities which have some predicted value, like this should be equal to 1 for well-behaved solutions, which we also tested. Okay, so this is what we achieved. This is a plot that summarizes all known solutions to these numerical solutions in level truncations. In different colors, we have solutions found at different levels, concretely level 2, level 4, level 5, level 6. And we plot, of course, the solution is like a vector in vector space of many dimensions, but here we somehow plot the solution, we label the solution by its energy. We look for complex solutions for good reasons. Well, first of all, on the real axis, there are much fewer solutions, but we are just interested in complex solutions, and then we can always focus on the real ones at the end of the calculation. So one of the reasons is that we might be interested in seeing like a family of complex solutions approaching a real solution at infinite level. So that's why we look to complex plane. And also the Newton's method and this homotopy continuation method works much better with complex solutions. So these are the starting points for the Newton method. So at level 6, I guess, if I remember, we have something like 30, is it 30 or no, maybe 20 equations in 20 variables, or more than 20, something between 20 and 30. So we would have the corresponding number to do something like maybe 26, which is a pretty large number of solutions. But only very few fall in this part of the complex plane with the real and imaginary part bounded, let's say, by 10. So most of the millions of solutions would be outside this range of energies. So we search both for solutions which were twist even. So this is a convenient ansatz if you want to go to as high level as possible, for example, for the tachyon vacuum, which you assume to be twist even. And these solutions are denoted by dots. Non-even solutions we denote by diamonds. And there is this additional SU11 symmetry, which I don't plan to discuss too much, but it's kind of a useful additional constraint that is preserved, or which is consistent to impose on the equation of motion. And for the singlet solutions, we have like these bigger symbols, and for non-singlet, we have like smaller symbols. So this is the legend behind this picture. And these are the results which I have, or which we have already shown, I think, at the previous string field theory conference. So if we take these starting points and we improve the solution, or we use it as a starting point for the Newton method at higher level, so the solution moves to some new solution, and then at another level, etc. And we were able to go to levels 26 for some, for the twist non-even solutions, to 28 for the twist even, to level 30 for the tachyon vacuum, which is real on top of each other. So to fairly high levels, we were able to improve these solutions. And if we fit the curves, we seem that it's quite obvious that they all go, the energies to a real value, at least close to a real value. I'm sorry for that. Okay. So the tachyon vacuum is this point here. So in this convention, we have some shift by 1 with respect to the original convention by Sen and Zwiebach. So for us, 0 is the tachyon vacuum. And the points here are so close to each other that you don't see this line, but you see just a single point on this thing, because all these things are within the... So this shows how just good the tachyon vacuum solution is. And of course, perturbative vacuum is at +1 exactly for all levels. But there are these 4 additional branches which we gave like nicknames. Here we don't put them in quotes, but on the next slide we will have quotes. Just we call this double brain because it Well, it would be double brain if it would go here. So maybe we should call it three half brain. This guy goes to like half ghost brain. This guy goes to like -1 pretty convincingly. So it's like a ghost brain, and there is another family of solutions which goes somewhere here asymptotically, which we call half ghost brain. Oh yeah, so this is the half brain, this is half ghost brain. Okay, so these are the results of the fits and the summary of these solutions. So you see like pretty nice precision for the two energies computed in two different ways for the tachyon vacuum. The nice thing is that the invariant which measures the other out of Siegel gauge equations is also very close to 0. So this is a really nice solution, the tachyon vacuum. Of course, a single brain is a trivial solution. There is nothing to say about that. And for these additional 4 solutions, you see that the ghost brain is both energies come like tantalizingly close to -1, like within like roughly 10% precision. Also, this out of Siegel gauge invariant is close to is like less than 0.1. So this is a very nice solution. But do they really exist as physical objects, the ghost brains? Well, we believe not, right? So it would make the theory inconsistent. But nothing prohibits us to see those objects as some saddle points in complex saddle points in the path integral as complex solutions. For example, in Minkowski space, the Young-Mills equations of motion have complex solutions which correspond just to Euclidean instantons, right? So sometimes these complex solutions do have some meaning, and this is what we propose how to think about these ghost brains. So the solutions are complex, and this is very nice. On the other hand, the double brain, which we think might be a physical object, so this is a solution which might get possibly real at infinite level, though the fits are not very decisive. But we see that these imaginary parts are kind of not that large, and you saw from the picture that everything goes towards the real line. So the main problem with this double brain solution is that this invariant is kind of big, and these two values don't quite agree with each other and don't quite give the value +2. But we believe that these issues are all correlated, and what that can mean that probably Siegel gauge is not the best gauge to find those solutions, but somehow we still take it as evidence that something like double brain might exist. And I just heard from Ted earlier during the coffee break that they actually constructed double brain solutions analytically in the universal sector. But this is unpublished work. So these objects do exist most likely, though in some analytic treatments they appear to be anomalous, and in the non-anomalous form they are still like rumors in the community, right? Then there are two peculiar brains that we thought at first that they shouldn't be there, but somehow just can't ignore them. They're complex. I mean, this pseudo-real. I mean, this is some peculiar property, but they're really complex, and they look like a Meronic objects, like with. Really like half brain or half ghost brain. So I have no idea what is the meaning of that, just that in gauge theory, barons also appear, and in the superstring field theory, analogous solutions were constructed. In the picture zero string field theory, analogous solutions were constructed by Ted Erler, and I think they created a lot of puzzles, I think. Yeah. So now let me move to non-universal solutions. So this is something we tried. Sorry, but in the universal, until now, I discussed the universal sector, which doesn't care about whether the space is compact or non-compact, because the space doesn't appear. The only thing which appears is like the BC ghosts, which do not care about space-time, and the total Virasoro generators of the matter sector. So now I will move to...
Because you mentioned Merons, and I thought the Torons and Torons existed only...
Yeah. So... Yeah, you should take it as more as an analogy, like from the point of view of path integral to have some saddle points. And, yeah. Okay. So after these non-universal solutions, well, we try to see what can. So how much of this technology applies to some concrete BCFTs, whether we can construct some useful solutions, and hopefully whether we can learn something about new boundary conformal field theories. So, and indeed, string field or open string field theory is a great tool to learn new and often surprising, very surprising things about boundary conformal field theory from a very novel perspective. So the basic setup is to consider open string field theory formulated on a background, which is a formally product background of two conformal field theories, one that you care of with center charge C, and one that you don't care about. And look for solutions which do not excite any primaries in this theory. This is not the fully sufficient condition, but it's like necessary condition. And a class of such solutions will describe new boundary conformal field theories, new boundary conditions for this part of the background. So in general, the boundary state can be decomposed in the Ishibashi state, which are in correspondence with spinless primaries in the bulk theory, and following the insight by Ian Elwood and Takahashi and Kishimoto and others, we proposed with Carlo Macaferri and Matěj Kuderna this formula for these coefficients. These are gauge invariant quantities from the point of view of open string field theory. And this is how we measure those. And we have just, so we use some trick by adding some auxiliary CFT and particular vertex operator by this Y and W. We put it on shell so that this invariant makes sense. But we can measure these coefficients for arbitrary primary. And surprisingly, this kind of formal definition works very efficiently for numerical solutions and can be programmed very easily. It's also interesting to note as a side comment that the boundary state coefficients defined like in this way, thanks to the linearity in the psi field or apparent linearity in psi field, can be shown to obey these classifying algebra relations known from rational conformal field theory. Of course, under certain assumptions. Okay, this is just a toy example that you can give to a bachelor student. Just take truncation to two string fields. Let's say for the Ising model, we have the identity matter field and epsilon matter field, and then we can plug it to the action and get something like that. Draw a picture of the potential in these two variables, find four critical points, which correspond to closed string vacuum, perturbative vacuum, and 2 points which correspond to the decay of the original sigma boundary condition or free boundary condition of the Ising to the fixed boundary conditions. And now Mirek is now moving to his first postdoc from Perimeter to Berkeley. So, of course, Ising model is a well-known model, but we can apply this technology to something more complicated, and already a free boson on a two-dimensional torus is a surprisingly complicated theory where exact results are not fully known. And we have discovered with Matěj Kudrna and Jakub Vošmera that there are some new boundary conditions that you can get by condensation of Z3 symmetric tachyon momentum modes. The endpoint of this relevant RG flow is given by some new boundary conditions. This is a profile corresponding of the energy. So if the endpoint was like let's say 2 D0 particles, that you would see only like 2 points here without these lines. If it would be like a D1 brane, it would be some, let's say, line like that, like a wrapping torus. But this is something kind of unexpected. And we will hear a talk about this by Jakub Vošmera. But actually, he will not discuss string field theory today. So for him, string field theory was just the motivation to look for these objects analytically. And he found corresponding solutions analytically in the framework of boundary conformal field theory using the Gepner model or Gepner model-like construction. So this will be the first talk after lunch, if I remember correctly. And these objects are not some particularities of some particular shape of the torus or radius. These are really generic objects, some new type of D-branes, either in bosonic theory or in superstring theory. So actually, Jakub will discuss the whole thing in the fully supersymmetric setup. Very nice piece of work. So this will be in the afternoon. So now I come to what I find the most beautiful part of the story of string field theory, which are the analytic solutions in open string field theory, arising from the mysteries of conformal field theory and the waves and the paddles of conformal field theory. Okay, so there have been many developments, and I will review some of those. So to find a solution to this infinite set of coupled equations in infinite variables, it's very useful to reduce the number of the observables to or the components of the string field to something smaller, to something manageable. And the most or the simplest example of such a structure is called a KBC algebra, which is like object algebra freely generated by three fields, K, B, and C, called. Toshiko Kojita reviewed their explicit construction in string field theory, but I don't need it for this talk. Just to remind you that these objects satisfy these very natural algebraic relations. And then in principle, given those algebraic relations, you can give it to high school students to try to look for, even elementary school students, to try to find some solutions just by playing with these objects. It's like a game. Okay, so we have these three objects with these relations. Then we have a Q derivative that annihilates K, takes B into K, and from C you get this CKC. Okay. Actually, you could find a solution without considering the B field. So it's just, this is a simplest example of the solution. So this background is blue because I keep showing this transparency since 2005. Okay, so I'm sorry for. So this is how it works. It's just very simple algebra. So the solution has one unfixed complex or real parameter alpha. Okay. So more general solution, which includes the B field, is given this one. It's not the most general solution in KBC, but it's a fairly general, and it's already interesting enough. And in this form, it was written down first by Yuji Okawa in 2006. So the question is what these solutions correspond to. So in 2011, with Masaki Murata, it's kind of embarrassing to say that it took us like 6 years to take the solution and plug it into the action. It was kind of not straightforward, algebraically tedious, but at the end, everything simplified, and we found a very simple formula for the energy. And you recognize this as being an integer invariant. So this naturally leads us to the hypothesis that these solutions might describe not only perturbative vacuum or tachyon vacuum, which differs by 1, but also some exotic multi-brane solutions with integer, positive or negative integer values for the energy. Oh yeah, so this is some loop in the complex plane. Yes. Yeah. So it's some specific loop. It's some specific loop in the complex plane. Yeah, it has to do with the representations of these functions, and it's independent of G. The loop, yeah. So I think it's like the right infinite semicircle. Okay. So, but unfortunately, this class of solutions is plagued by anomalies in equations of motion, and some people like Hiroyuki Hata and Toshiko Kojita seem not to worry about that. Some other people seem not to worry about that either, but I think all nice solutions should obey the equations of motion when constructed with Fock states. Especially that's the necessary requirements for any solution that's supposed to work numerically. Otherwise, you would not ever be able to find a solution numerically or verify that it is a solution. So I think the research is still on these type of solutions. So one thing we tried with Nick Mertes, who was at the time a visiting summer student, we tried to generalize the KBC to more fields, to more objects, and we found some objects which we called these L string fields, which turn out to obey, interestingly, Virasoro algebra with zero central charge, but these are string fields and these commutators are with respect to the star product. And we were able to find like one example of a nice solution, but I think this was just a short summer project, so there are many more things to be done to check the various properties of the solution and generalize it to further and maybe find something interesting there. So this is just a hint of what can be done more than a solid. Well, the result is solid, but so far not very useful, except for the fact that these string fields obey this nice algebra. Okay, so there are other solutions that appeared in the literature, in very interesting solutions. So for instance, the Masudanumi Takahashi solutions from 2012, which is of a different form, which doesn't take a simple like product structure. It's not in this Okawa form. It has actually two terms like that. And it's a solution provided this f times h is 1. And it seems to describe a ghost brain. But unfortunately, because of this condition, one of these two fields must be too identity-like, and therefore the solution is plugged by some divergences, at least in Fock space expansion. And I think this is desirable for the solution to be sick, because you see that the solution is otherwise real, and we don't expect any real solutions for the ghost brains. There is another solution that was, as quoted in this paper by Jokel in 2017, was found by Ted Erler, and he just told it to him. So the most general solution can be found in in this form, where T is some object of ghost number 1, something like a generalization of C. So you can call it KBT algebra. Okay, so it's like for zero momentum tachyon vertex operator, and this is like the only non-trivial relation that you need to show. And supposedly all known solutions fall in this class of solutions. So there have been very little progress following up on this observation as far as I'm aware. Okay, so now coming to non-universal solutions and attempts for analytic constructions. So the non-universal means that we try to answer some question pertaining to the boundary conformal field theory in question that is governing the brain that we are working with. So for exactly marginal deformations, so typically we try to add one extra operator, which we call J, for solutions describing a generic background changes triggered by some boundary condition changing operators, sigma and sigma bar. We would add some two new string fields. And for the superstring, we had to add also like a, let's say, gamma ghost, and also this Q sigma and Q sigma bar has to formulate two new objects in the algebra. So for the exactly marginal solutions, so this is like the minimal useful ansatz. Well, of course, except for the CJ solution, which is similar, where you don't need either K and B. Okay, so when we have a broadsheet operator which has a finite OPE with itself, which is quite uncommon if that operator has dimension 1, but there are known examples where this OPE is finite. then the resulting solution can be written down like in this form. Again, so f is a function of k, and so this is a formula from 2007, so this is very simple, so it was found very early on. For the typical case where where the OP is singular, you have to be much more sort of inventive, and so there are various attempts or procedures to deal with this issue. So either you can use a like elaborate subtraction procedure by Kiermaier et al., which I think was sketched and worked out explicitly to something like third order, if I remember. Or you can use some other approaches where instead of this insertion of this worldsheet operator on the identity strip, as you would do for C, you use the integrated version of this operator. And either you integrate horizontally, as in this paper by Fuchs, Kreuter, and Putting, or you integrate vertically, as McAfee did in 2014. Or you can abandon this framework altogether and use approach by Kiermaier and Okawa. It's kind of quite complicated. So since Erler-McAfee solution has been very popular in the past 5 years, so let me review it here. So this is a solution which describes or which shows, which proves that there is a classical solution in open string field theory corresponding to any new boundary condition. So the idea is to start by doing something like a formal gauge transform of the tachyon vacuum. So think of it as expanding the theory around the tachyon vacuum. And if this sigma was just identity, then the whole thing would be zero. This would be the perturbative vacuum. But by rotating this psi, you don't go back in general to the perturbative vacuum. Instead, you find a new boundary condition. So formally, the equations of motion are satisfied provided that these two or these three conditions are satisfied. So satisfying these two conditions is easy. You can just take sigma and sigma bar to be Q of something. But this condition is more tricky. But kind of miraculously, Erler and McAfee found that you can take that for this choice, and this choice of the tachyon vacuum is in this Okawa form. For this choice, the sigma bar sigma is equal to 1, provided that this little sigma bar sigma are equal to 1, and yeah, they are just something like purely matter objects. This condition is quite tricky to obey in conformal field theory because the standard boundary condition changing operators give you divergences when they appear close to each other. So they dress this by they dress these sigmas by some time-like factors. In a recent work in this year, together with a student Norris, they argued that for f of k, which behaves as some power of k, which is negative and smaller than -1 for k going to infinity, various singularities cancel that it becomes a valid solution even in the case of the superstring. Of course, this is not a complete solution for the case of superstring, where you want to go, let's say, in the context of Berkovits theory, to find the Berkovits string field phi, or like the gauge gauge element corresponding to this connection, and this has not been achieved. But anyway, this is a good starting point for the superstring field theory case. There has already been a useful and interesting application of this solution that was in a paper by Nobuyuki Shibashi, Isao Kishimoto, and Toru Masuda, and Tomohiko Takahashi, where they described a solution corresponding to a magnetic flux on a D-brane, starting with a D-brane with no magnetic flux. So what about the spring field theory and the super spring field theory? So this is some already now 5 years old result by Ted Erler. So in the Berkowitz theory, which takes this form, so you can solve this equation in the small Hilbert space, and so you can find a solution, let's say of this form. But then the non-trivial thing is to find this. If you know this object, is to find this e to the phi, what that is, and here I call it G on this slide, and he found that that this G can be written in this form and G inverse in that form. So that means that this GQ G inverse is equals this psi. So this object is in the small Hilbert space, whereas this G and G inverse are necessarily in the large Hilbert space. So they contain this inverse of the bosonic ghost gamma. If this object was not in the small Hilbert space, then this would mean this would be a pure gauge. Okay. So he computed the energy, which was quite an elaborate calculation, and everything works very beautifully. Okay, so now I'm coming to the end of this talk. So let me give you a summary. But instead of giving you a summary of a summary, let me give you a list of the open problems. So the open problems in the open bosonic string field theory, the most beautiful one, are like one of the problems is to find a nice, well-behaved, anomaly-free solution for multiple branes, and if the rumored result by Ted Erler is true, so arguably, I mean, you can find something even nicer. So that solution apparently is larger geometric, contains some blobs of surfaces, as far as I understand. So maybe you can find something that would be more algebraic. Anyway, anything is good for this. One of the outstanding problems is also to find a well-behaved, anomaly-free solution corresponding to generic RG flow. So if you are given a BCFT with a relevant operator, so can we find an endpoint for this RG flow? So some interesting step forward was given by Bonora, Macaferi, and Tola in 2010. And they obtained some rather miraculous results for that solution, getting the right invariance of the solution. But we had a friendly argument about the validity of the solution, since it doesn't seem to obey the equations of motion with respect to Fock states. But this is, again, sorry? Okay, anyway, so this is one of the open problems. I would say, to convince the others at least that you're right. So in open supersymmetric string field theory, so one can look for an analogous analog to the Erler-Macaffery solution in the context of the Berkowitz theory for the group-like element G. And also there is like a very interesting controversy going on these days about the issue of marginal deformations of the coincident D0, D4 system. And we will hear more about this in the talk by Ivo Sachs and the following discussion. So in the closed bosonic string field theory, which is only very sketchy, which is a rather unfinished story. So we are missing an analog of sense conjectures which we could use to interpret the closed string field theory vacua. And also we are lacking good observables. So it's known that in closed strings there are no local observables, but we need some observables to make sense of these classical solutions that we can find in level truncation. One minor problem might be to understand the action of defects on closed strings, and in the last conference in Japan I had some proposal to enlarge the space of string field theory by adding some disorder operators in the asymptotic states or in the Hilbert space, and then the action of defects becomes rather non-trivial, and this might lead to interesting structure like Chen-Payton-like Chen-Payton-like structures for closed strings, but this is something that I don't want to speculate too much about it. And another thing, another very important problem is whether we are confined to Witten vertex, because in recent years, especially following the works by Ashok Sen and his collaborators, we've seen that we can do many new things with string field theory when we just don't confine ourselves to the Witten vertex, and it's a very complicated geometry of the local coordinates, and especially the coordinates for the higher order vertices. So maybe can we construct these solutions using some other types of vertices that would obey this L infinity algebra? So these are some very interesting things. And for the closed supersymmetric theory, I have nothing to say. It's just a piece. Thank you.
So we have time for a few questions.
Yeah. Wow. I like to impose stronger conditions unless I'm forced to do otherwise. So in elementary, like engineering, mathematics, when you solve differential equations, you want your equations to be satisfied in a generic class of, in generic spaces, let's say L2 spaces or something like that, and not in some spaces which are just obtained, let's say, by multiplying by some other functions. Because, for example, when you take a delta function of x and then you multiply it by x, it just disappears, right? So you would have, in many cases, you would not have the solution to the original problem, right? So you would lose some information. So I don't want to lose some information, so that's why I impose stronger conditions. Yeah, well, I mean, we might be forced eventually to do what you suggest, but I'm resisting. Sorry? Well, I've heard the best opinion from you. Yeah, so your proposal that the authors miss the possibility of some second order perturbation to the deformation, I think is like the best way out. So.
Isn't there an issue of relaxing the radiation constraints on which you raised, you and Yaku? Doesn't that solve the problem? I want to know why that solves the problem.
Okay, I think, is Ivo here? Ivo is not here. Okay, so I admit I prefer to discuss this question in private or in after, or when Ivo is here. Yeah.
Okay. Oh, we have time. Take it easy. Just have to check all the connections.
Is it working? Okay.